Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Thoriq Alfarizi and my student number is 22060555265. And I'm here to talk about optimization, especially in fluid mechanics. So, optimization in fluid mechanics involves finding the best possible solution to a problem related to the behavior of fluids, such as air or water, within a given system. And this could include maximizing efficiency, minimizing energy consumption, or achieving specific performance targets. And let's break it down. The process of optimization in fluid mechanics into four key components, with in mind of the intention, initial thinking, idealization, and instructions. Okay, first, intention. The intention behind optimization in fluid mechanics is to improve the performance or behavior of a fluid system according to a certain criteria. This could be to enhance the efficiency of a pump, reduce drag in a flow, or increase mixing in a reactor. So, this intention guides the entire optimization process, defining what aspects of the fluid systems need improvement and what goals need to be achieved. And what Pak Dai told us that the intention is to solve the problem with for the sake of God. So that's what the main point of intention is. And the second one is initial thinking. So before diving into the optimization process, it is crucial to have a clear understanding of the problem at hand. So you need to analyze the problem first so that we have an initial thought, and this involves defining the objectives, constraints, and variables involved in the fluid systems. For example, in designing an efficient pipe network, considerations might include flow rate, requirements, pressure drop limitations, and material constraints. Initial thinking also involves selecting appropriate mathematical models and optimization techniques to tackle the problem effectively. And the third one is idealization. Idealization involves simplifying the complex reality of fluid dynamics and into manageable models that can be analyzed and optimized. This often entails making assumptions and approximations to reduce the problem to its essential components while capturing the key phenomena behind fluid behavior. For instance, in analyzing airflow over an aircraft wing, idealization might involve assuming a steady, incompressible flow and neglecting viscosity effects for simplicity. Idealization helps in formulating mathematical representation of the fluid systems, which are essential for optimizations. So, in other words, um, idealizations helped us to make a better understanding of the problem by simplifying it. By simplifying it, we can solve the ideal answer to the problem, and if it has another complex problems, we could use the fourth one, so which is instructions. So once the problem is defined and the models are selected and the system is idealized, the optimization process begins. This typically involves iterative steps of analysis, simulation, and adjustments to find the optimal solution. Instructions for optimization includes defining objects functions that quantify the desired outcomes, e.g., maximizing lift to drag ratio, setting constraints to ensure feasibility, e.g., maintaining a minimum flow rate, and selecting appropriate optimization algorithms to search for the better solutions within the defined parameter space. And instructions also involve interpreting the results of optimizations to understand how changes in design and operation conditions impact the performance of the fluid systems. In summary, optimizations in fluid mechanics is a systematic approach to improve the performance of fluid systems by defining intentions, engaging in initial thinking, to understand the problem and idealizing complex systems into manageable models and providing clear instructions for the optimization process. Through this process, engineers and researchers can develop more efficient, reliable, and cost effective fluid systems to meet various practical needs. So that's it for optimizations in fluid mechanics. I hope you enjoy it. Assalamualaikum warahmatullahi wabarakatuh.